It was going guys, xiangqi here. Last video we ended up by looping over the board squares, and in this one it's time to distinguish between those squares that are on board and those squares that are off board. So just to give you an idea what am I talking about, so we're using here a so-called hexadecimal 88 board representation, which allows to distinguish between those squares that are on or off board by using a single bitwise AND operation with a constant of hexadecimal 88. So here, the leftmost 64 squares are standing for the board itself with the pieces. So first two lines are the pieces here as well, and this part is just the p-square table, which would gonna be used later for the evaluation purposes, like positional evaluation. All right, so our goal is to debug somehow the logic of distinguishing between these squares, because once we're able to consider only those squares that are actually like on board, this one, then we can pick up pieces there and make sure whether the piece belongs to the certain side to move, whether it does or not. But another little update that I made. So in order to avoid uploading partially like the variables to the 0 page and the program to the address of hexadecimal 200s, I just added this fake RAM bytes. So this is the memory byte I've taken from the emulator's memory. I'm not sure if I keep this in the eventual version, but probably not. But for debugging purposes, it's quite nice. It's quite nice to have one because it allows me to change something here within the code and then re-upload everything. And because every time I re-upload things, it just clears the memory and resets the CPU in order to avoid losing this board, in order to avoid clicking tons of times to upload this twice. I just made this tiny little hack here. So without further ado, what we're going to be doing, we're going to be running this code now. So what has changed since the last video? Well, apart from bundling the data and the code, like data segment and the code segment into single file, and I'm just distinguishing between those by this fake memory dump here. So what we're gonna be doing here, so here is our loop over the board squares. So two most essential lines are here. So we are bitwise ending whatever we have in the A register, and by this time either it comes to the loop for the very first time, it's containing 0, which is the initial value for a square, or if it comes from the loop from the previous iteration of the loop, still A register contains the value that has been just incremented in the stack memory. So anyway, we have this at this point we have A register being equal to this to the value of the source square, which means that we can use this single bit operation to bitwise and with the value stored in the offboard. So I've added a new variable here because I didn't know that it doesn't support the direct addressing, like immediate addressing mode. It just supports this absolute and someone else, not sure, but anyway. So here is the offboard, and here we have this is the label, and here we have the value of hexadecimal 88. So literally what this line of code does, it compares the value currently available at the A register, which stands for current value of the source square, with a constant of hexadecimal 88. In case if it's not equal to 1, so if it's equal to 0, so branch not equals, okay, hold on a sec. If the bitwise operation results in 0, should be, yes, if bitwise operation results in 0, this not here, in this case, I just stuck a little bit because branch not equals means branch not 0. So I can't say for sure what exactly happens to the 0 flag here, whether it's being set or not. But instead of trying torturing my brain, and I like I always like to joke that why do I consider programming as a career, because I don't need to think there. So yeah, thinking is not my best ever. skill. So I just want to demonstrate how easily we can debug this by trial and error method. So at this point, after we transferring the value of a register to x now equals to the source square, and it serves as an offset. So now we're loading just the random value of AA, just this is not the random, just the marker value, let's say, to the A register, and setting this value at board plus the offset x. So x is square at this moment, so board plus square, while the square is now lives in the x, and the board is just to label. Actually, that's the 0 page address 0, so that's the very first byte. So from the very first byte, add in whatever we have in the variable source square. That was in A register, then it gets transferred to the X register, and then it gets added to this board, to the address where the board is. So let's assemble this. Now we want to start it from 0 and upload, and 0 to 0, 0. So the address to start running the program from is still the same. Before running the program, let me just quickly show you the hex dump. So I now want only to print 16 bytes width, because now we can nicely see our board. So our board ends up here. So we have the black pawns here, the white pawns here, like white pieces, black pieces, and the p-square table. So now we need to consider only the half of the board, and we will actually mark the half of the board with this AAs. Well, obviously, in a real program, this won't work because we just malformed the entire board position. But for now, just to make sure that our logic of considering only those squares that are available on the board, this is fairly enough. So if I just say Control G to run this and have a look at the hex dump again from 0 to, let's make it 316. Now, not surprisingly, but instead, as expected, we have all the 64 squares that are actually on board. They has been marked with this AA because these are the exact squares that we're gonna be working with. So otherwise, it just from here. Otherwise, if the square is on board, it doesn't get into the main code. Instead, it just jumps to the next square and increments the square. And just to give you an idea, to make this on the countries, if I just say branch equals instead, and do exactly the same thing. In this case, it would consider the offboard squares actually, and mark those as well. So okay, hold on a sec. Again, 0. Upload 0 to 0, 0, run, hex dump 0, 16. So now you see, like, here I'm considering only offboard scores, but obviously that's not what we actually want. So just drop in back to branch not equals and assemble 0, upload 0 to 0, 0, run, hex dump 0, 16, and here we go. So now we did have considered only those squares that are on board. So from now on, we can distinguish between white and black pieces, pick up the pieces, storing the piece type, piece type, all the stuff that is needed within the moving rate. This is it from my side, guys. Thanks for watching. Until the next time, and take care.